Alright, so in this next lecture, I would like to talk about how elements are arranged in either series or parallel. So every element, whenever it is connected to another, it is sometimes in one of these two configurations and sometimes in neither of these. So I'll first talk about series. The elements in series, they always have the same current going through them, and the elements in voltage always have the same voltage across them. The reason I use the term across is because the voltage or potential difference is always between two nodes between which the element is connected. So a simple example of a series circuit is this. If this is a circuit, clearly there's just one path for the current to follow, one path for the coulombs to go to, and this is just the single path, and obviously the current would be the same too because there is nowhere else the charges can go. So if there are 2 coulombs per second going through here, there would be 2 coulombs per second going through here too. And so all of these elements, they are in series. However, if I have a voltage here and I have a resistor here, this single node pair circuit, as discussed in the previous practice example, there are just two nodes, node A and node B. All of the elements are connected between these two nodes, and hence the potential difference across each element is the same, which is basically VA minus VB. So this is what a parallel configuration is. Sometimes it is pretty easy to see how the current is the same in all elements or the voltage is the same across all elements, but sometimes it gets difficult when the circuit becomes a little too complicated. So the easiest way to see if an element is in series or in parallel is shown in the next example. So as we are relating all our laws to nodes or loops, we'll just relate this configuration law to node 2. So a series circuit by definition is two elements are always in series when they're connected to a node which is not connected to a third element. So for example, I'll just mark all the nodes in this circuit. This is node A, this is node B, this is node C, and all of this is node D. So if I look at node A, there is just this battery and this resistor R1 connected to it. So because there is no third element, these two are in series with each other. If I look at node B, node 1 and node 2 are connected to it. There is no third element. There are just two elements connected to this node. So these are in series too. However, if I look at node C, even though it looks like node 2 and node 4 are in series, but as you can see, there is a third element connected to this node. So they are not in series. Then if I look at node D, there are a total of 1, 2, and 3 elements connected to it. So these are not in series too. So the way to look at it is that if you want to know if two elements are in series, just look at a node they are connected to and see if there's a third element connected to it. This is how you can see if they are in series. Now, the traits of a series configuration. The first one is that the current is always the same through both elements. The second thing which would come in handy sometimes is that you can replace elements in series. Replace elements. For example, if resistor 1 and resistor 2 are in series, I can draw the circuit by putting the resistor 2 here and resistor 1 here. You can just interchange their places and it would make no difference to the circuit because they are in series. Number 3 fact is that uh, the voltage sources in series add up. You can add the voltage sources in a series configuration. If there are two voltage sources, you can just add them up, and I'll show why in the next example. And the fourth point is that the resistances add up too. Now, in the next example, I'll show why this is possible using a proof. If I have this circuit, as you can clearly see that it's a single loop circuit, and all the elements are clearly in series. There's this node R1 and R2 in series, R2 and R3 in series. As R2 and R3 are in series, they are also in series with R1. So if I just write the KVL here, and I can just use this current, I can see that it is minus V. We can start off from here. I see the negative sign first, then I can write I R1 plus I R2 plus I R3 is equal to 0. If I simplify this, I can write plus V plus I, and I can take I as common, and I can just add up the resistances. As you can see, this thing, that means I can draw this circuit as this too. It would yield the same equation. So resistances in series can be added up and form a single resistor. So this is an important point. Just add up the resistances in series and you can get your new resistance, and you can combine all the resistances into one. So combining resistance in series means you can just add them up. The second point is that the voltage sources in series also add up, and I'll show you why. As you can see here, if I apply the KVL from any point, I can just start off from here. I can write, I can move clockwise. I write IR plus 3 minus 2 is equal to 0. And that would mean IR plus 1 is equal to 0. As you can see, I just combined these two voltage sources into one. I just added them up according to their polarities and I wrote them as one. So voltage sources in series can be combined by just adding them up and putting the polarity as of the voltage source which has a larger value. So the 3-volt source has had the larger value, so I can just draw this like this. Just draw the 3-volt source like it is and write 1 volt because this is the new value, and then R here, and you can just combine them. So this, in a nutshell, you can combine voltage sources and resistances in series by just adding them up. This is what a series connection is. The important thing to note is you can interchange places in a series circuit. You can just look at nodes and see if the elements are in series, and if they are, they have the same current passing through them, so you can just interchange their positions. So for example, you can put the voltage source here and the resistance source here. That wouldn't change the circuit. Now moving on to the parallel circuit. So by definition, the parallel circuit is a configuration where the two elements in parallel, they are connected between the same pair of nodes. So the first step is just mark all the nodes in this circuit. This is node A, this is node B, this is node C, and this is node D. Now just look at each element. Do you see any element that is connected between the same pair of nodes? As you can clearly see that element 2 and element 3, they are connected between B and D, so they are in parallel. So just write them 2 and 3 are in parallel. So this is how you identify if two elements are in parallel. Now these two elements, they would have the same potential difference across them because they are connected between the same pair of nodes. Even though it might look at it in the first glance that element 5 is also in parallel with these, but as you can see, element 5 is connected between node 5 and node C and node D. So that means it is not connected between the same two pair of nodes. Now there are some traits of a parallel configuration. The first one is the voltage across each element is the same. The second important thing to note is that the resistances don't add up. They are added up in this manner. They are combined in this manner. Now I'll show in the next example why. The third point is the current sources in parallel add up. Now let's see why. Okay, so now if I look at this circuit, I can see that there's this big current I going, and there's a current in each of these two, I1, I2 and I3, let's call it that. If I apply KCL at node A, I can see that there's big I entering the node, there's I1 leaving the node, there's I2 leaving the node, and there's I3 leaving the node, and that is equal to 0. Because I've taken the currents as going downwards, that would mean that this is the positive terminal, this is the negative one. So A is the positive terminal and B is the negative one. So I is equal to I1 plus I2 plus I3. But using Ohm's law, we can see that basically the voltage across R1, we can use the Ohm's law to write I1 as VR1 divided by R1, and I2 as VR2 divided by R2, and I3 as VR3 divided by R3. But as we can see that VR1 is basically the voltage between node A and node B. VR2 is the same too. VR3 is the same too. As I told in the previous example, that the voltage across parallel elements is the same. So we can write all of these as VR1 plus V over R2 plus V over R3. That would mean I can take V as common and just write 1 over R1 plus 1 over R2 plus 1 over R3. This clearly means that the combined resistance or the equivalent resistance is just 1 over R1 plus 1 over R2 plus 1 over R3. Sorry, the basically the reciprocal of the combined resistance, because I this is basically 1 over R equivalent. So the reciprocal of the combined resistance is basically the sum of the reciprocals of all the resistances in parallel. This is how you add up or combine resistances in parallel. Now let's look at how current sources add up in a parallel circuit. Now as you can see this circuit, there are two nodes A and B. All the current sources are between A and B, so they are all in parallel. So the way I can add them is I can apply KCL at any node. I can apply KCL at A and I can just add them up. There's 2 amps entering node A, so it's plus 2. There's 1 amp entering node A, so plus 1. And there's 5 amps leaving node A, so it's minus 5. And then there's a current going into the resistance, so it's minus I2 is equal to 0. If I look at this is minus 2 minus I is equal to 0. What I did essentially is I added up all of these three current sources and I just use the KCL to add them up. So this is how you add up current sources in parallel. Just add them up and put the direction of the larger current source. So this is how you use the current sources in parallel. So in summary, the point to take is that whenever you are given a circuit and you want to combine some elements, or you want to make the circuit more compact, just mark out all the nodes in the circuit and see which elements are in series and which elements are in parallel, and then you can combine those resistances or you can combine those elements to form one. I'll just show an example of a circuit and then I'll try to use these configurations to solve it. As you can see, this circuit, we'll just mark out the nodes. This above is entirely node A and this below is node B. So you can see that all of these elements are in parallel and we need to find the voltage across this resistance 10. Now the first point to note is that the voltage across this resistor is the voltage across point A and point B, and hence this is the voltage across each element because the voltage across each element in parallel is the same. The second point to note is that whenever we are given a parallel circuit, we can interchange the positions of each element because that wouldn't matter here. So let's just put all the current sources to the left and all the resistances to the right. So it would form a simple looking circuit. This is 1 amp and this is 6 amps, and then I have a resistance here and a resistance here. So I just took the 10 ohm resistance and I put it here and I put its current source here. The first thing to note is there are three current sources, so they can be added up. So I can just add 5 and 6, 11 minus 1, so that is 10 amps with an up direction because the larger current sources are above. So I just add up the current sources. The second thing is I can combine these two resistances into one. The way to do is 1 over R equivalent, the new resistance is 1 over 10 plus 1 over 10, and that would mean 5 ohms. So this resistance would be 5 ohms. Now these are still node A and node B, and I needed to find the voltage between these 2 points. Now the circuit looks very simple. There is a 10 amp current flowing into the 5 ohm resistor. So VAB is equal to just 10 times 5, which is 50 volt. So as you can see that whenever you combine resistances and whenever you combine sources in series or parallel, it becomes very easy. So now let's look at another example of a series circuit. Now I'm given this circuit which has a combination of series or parallel combinations basically, and I need to find this voltage V. The first step is let's just mark out all the nodes. So this entire thing is node A, this is node B, this is node C, and see, look at this little thing is node D because there is no element here, and this is between two elements. So now let's look at if we can find some series connections here. Clearly there are just two elements connected to node D, so this 2 ohms resistor and this 2 ohms resistor, these are in series. There's just two connections at node B2, so this 10 ohm resistor and this 10 ohm resistor, they are in series. So let's just add these resistances up. As we know that the resistances in series, they add up just by a mathematical addition. So we'll just draw this new circuit here, and these 2 ohm plus 2 ohm resistance, that is 4 ohms, this is 4 ohms too, this is 3 amps, and I need to find this voltage, and this is 4 amps. And clearly when these two are added, that would make it 20 ohms. So now the circuit looks similar. Let's just mark the nodes again. This is node A and this is node B. There are just two nodes. Everything is in between these two nodes, and everything is in parallel. So let's just interchange the positions so the current sources are together. So that would make this, I'm sorry for my writing. This is 3 amps, this is 4 amps, then there are 3 resistances, 20 ohms, 4 ohms, and then 4 ohms. Now, the first step is these, the two current sources, they can be added. This one and this one, they can be added, and that they would form a 7 ohm new current source. Now, if I want to add these three resistances, what I can do is I'll just use the formula 1 over R equivalence, the new resistance, 1 over 4 plus 1 over 4 plus 1 over 20, which would make R equivalent to be 1.82 ohms. Now let's draw our new circuit. I'll just clear this up. So as we had 7 amps current source here, and 1.82 ohms resistance here. Now I needed to find this voltage between node A and node B. So I'll just now this circuit looks very similar. So I just use Ohm's law and multiply 7 times 1.82, which makes it 12.74 volts. I hope I did not make any calculation error, but this is how you solve it. Just write out all the nodes and just start off by combining some elements into one another, and then at the end just find one value. So this is why series and parallel configurations are important. But one thing to keep in mind is that sometimes two elements would not be in series as well as in parallel. For example, this resistance and this resistance, they're not in series because at this node there are three elements connected, and so they're not in series. And also they're not connected between the two same pair of nodes, so they're still not in parallel. So some elements can neither be in series and not in parallel. So this is something to keep in mind. However, this is the entire crux of the series and parallel configuration.